Find all asymptotes of f of x equals the rational function 5 plus 2x squared over 2 minus x squared. First, we rewrite the function so that the polynomial in the numerator and the denominators start with the leading terms. 2x squared plus 5 over negative x squared minus x plus 2. We notice that the degree in the numerator, 2, is the same as the degree in the denominator, and so as x goes to infinity, the leading terms will determine the end behavior of the graphs. 2x squared over negative x squared will cancel out x squared, so we end up with 2 over negative 1, which is negative 2. And so we have a horizontal asymptote y equals negative 2. The trick is that if the degree of the polynomial in the numerator is the same as the degree of the polynomial in the denominator, then the horizontal asymptotes is the ratio of the leading coefficients. The coefficient in the numerator is 2. The leading coefficient in the denominator is negative 1. So the horizontal asymptote is 2 over negative 1. But only if the denominator and the numerator have the same degree. Next, we find the vertical asymptotes. The first step is to determine the possible candidate of the vertical asymptotes. The possible candidate for the vertical asymptote is where the denominator is 0. But again, this is only the possible list of the vertical asymptote, not yet the vertical asymptotes. The denominator is negative x squared minus x plus 2, and we set it equal to 0. To solve for x, we will attempt to factor this. Usually when we factor an expression, we want the leading coefficient to be positive, so we would factor out negative 1. What left inside is x squared plus x minus 2. And then we divide it by negative 1 both sides of the equation to obtain x squared plus x minus 2 equals 0. This is a trinomial, so we will use trial and error to factor this. X, we're looking for two numbers so that when we multiply, we get negative 2, and when we add, we get positive 1. And so the two numbers have to have the opposite signs. They are 2 and negative 1. So we should always double check the factor if we were to use trial and error. X times x is x squared. X times negative 1 is negative x. 2x. 2x minus x was 1x. And then 2 times negative 1 is negative 2. And so the possible vertical asymptotes are x equals negative 2 and x equals 1. But we still need to check. The only way to get the vertical asymptote is when x approach these possible candidates from either the left or the right hand side, the function increases or decreases without bound. Meaning, if we check that x go to negative infinity and the function f of x approach either positive or negative infinity, then we will end up with a vertical asymptote. To check if x equals negative 2 is the vertical asymptote, we draw a number line, label x equals negative 2, and we check the numbers that is close to negative 2, but not negative 2 itself. And so at x go to negative 2 from the left, think of these as x equals negative 2.1 or negative 2.01 or negative 2.001 and so on. We can also check at x go to 2 from the right hand side, which is negative 1.9 or negative 1.99 and so on. And so At x go to -2 from the left-hand side, for example, we'll pick one x value that is very close to x equals -2. The factor form of the function is 2x squared plus 5 over negative. We factor the denominator to x plus 2 times x minus 1. And we will evaluate this function at x equals -2.001, preferably a number that is very close to -2. We cannot plug in -2 because if we do that, the denominator will be 0. When we plug in -2.0001 into the function, we have 2 times -2.001 squared plus 5, that is the numerator, divided by negative, don't forget the negative sign when we factored it out, -2.001 plus 2 times -2.001 minus 1. Now, the numerator is a positive number, and it will be a number that is not close to 0 for sure. -2 squared is 4. That is very close to 4. 4 times 2 is 8. 8 plus 5 is 13. So that is the numerator, very close to 13. In the denominator, we have a negative sign, and then -2.001 plus 2 is a very small negative number. -2.001 plus 2 is almost 0, but negative. And then times -2.001 minus 1 is still a negative number. And so we have a negative sign times a very small, close to 0 negative number, times a negative. And so the sign in the denominator will be negative, and the denominator is a very small number, negative, very small. And so 13 divided by a very small number is a very large number, which is still negative. And we denote a very large number at infinity. And so we say that at x go to -2 from the left, the function goes to negative infinity, meaning it decreases without bound. And this is the definition of the vertical asymptote. And so we have a vertical asymptote at x equals -2. Follow the same technique and check if x equals 1 is a vertical asymptote by drawing the number line and label x equals 1. We then pick a number that is very close to 1, either on the left or the right hand side, and then we check the function f of x. F of x is 2x squared plus 5 over minus x plus 2 times x minus 1, and we evaluate this at 1.001. The numerator is 2 times 1.001 squared plus 5 over, the denominator is negative 1.001 plus 2 times 1.001 minus 1. 1.001 squared is 1, almost. 2 times almost 1 is 2, and 2 plus 5 is 7. In the denominator, we have a negative number, and we have a positive 3.001, and then we have a positive that is almost 0, very small. And so negative sign times 3 times a number that is almost 0 is negative, and it is a very small number, almost 0. And 7 divided by a very small number is a very large number. In this case, the sign is negative because 7 divided by a negative number. And so we say that the function decreases without bound at x go to 1 from the right, and so we have another vertical asymptote x equals 1. At this point, you might say, why do we bother with checking to see if the vertical asymptotes are the zero of the denominator? Well, there are some functions where not all zeros in the denominators are vertical asymptote. There is a trick here to identifying the vertical asymptote right away, and that is if we can also factor out the numerator and factor out the denominator. If we have a common factor and they canceled out, then the zero in that common factor is not a vertical asymptote. But the only sure way to check that the zero is a vertical asymptote is that the function increases or decreases without bound, meaning it's go to infinity or negative infinity.